In this video, we're going to talk about a cool application of Michaelis-Menten kinetics, and that is to actually learn about biochemical mechanism. So it turns out enzymes are actually common drug targets, and we'll actually hit a variety of them in this video. But one of the issues that often comes up is you either designed a drug that you think works a certain way, or you found a molecule that you isolated from some strange bacterium that has some effect on a cell, and you want to understand what it's doing and how it's doing it. And one of the major ways that biochemists actually figure that these things like this out, like how is the drug working, is by asking how does it alter Michaelis-Menten kinetics. And so, quick review of Michaelis-Menten kinetics. It's this expression here that models reaction velocity. How fast is a reaction going under a certain set of condition? And it does so by asking four questions. How much substrate is around, given by this S naught, the concentration of substrate? How well does the enzyme recognize substrate? It does that via Km, which is basically the same thing as a Kd for substrate binding. Basically, what is the affinity of the enzyme for substrate? It's how fast can the enzyme catalyze the reaction when something bound. That's called Kcat. So that's the rate constant once the enzyme is fully loaded up with enzyme. And then there's just how much enzyme is around, the total enzyme concentration. And quick, just to make sure we're reviewing this, that the Km measures substrate binding affinity, where the Kcat measures the catalytic rate once the substrate binds. Those tend to be the two most important things that describe the function of the enzyme, because E total, that's something that we or a cell can control. Same with substrate concentration. Again, how much is the cell making or how much did we add? Km and Kcat are instead fundamental features of the enzyme itself that determine how it works. Wrong button. So we can extract Km, Kcat, and Vmax from a curve. And just a quick reminder of this is S naught, this is V naught, this is the initial velocity of a reaction started with a known quantity of substrate. And this has the following shape where it saturates over concentration. Turns out that we can extract all of these values from this. So first, let's talk about this at the top. This is basically the maximum velocity that this reaches. This is the Vmax. And that Vmax is equal to the enzyme concentration total times the Kcat. And the reason that that's true is because we have this expression, V naught equals S naught over S naught plus Km times E total times Kcat. So when we completely saturate, when we reach the highest possible velocity, that's occurring when this number is 1, which is happening when the system is entirely saturated. We have no more enzymes left. So we're left with just this block here as the maximum total velocity. This expression here gives us the Km or the Kd. And Kd, what you do is you find 1/2 Vmax, and then you drop down and say, what is the S naught that gave 1/2 Vmax? So it's got units of concentration. It's a measure of the affinity of the enzyme for its particular substrate. Okay, so that was a quick review of Michaelis-Menten kinetics. Now we're going to talk about 3 different mechanisms an inhibitor might have of an enzyme and how that's reflected in the Michaelis-Menten kinetics. So first, competitive inhibitors. So HIV protease is critical for the maturation of the virus. And antiretroviral drugs actually bind at the active site. So this right here is the HIV protease bound to its normal substrate. This is it's bound to its drug. And it turns out that these drugs are acting as what's known as a competitive inhibitor. A competitive inhibitor binds at the active site, competing with substrate. So going back slide, inhibitor, substrate, same location. If the inhibitor is bound, the substrate can't bind. What this leads to is an increase in Km. How does that look? So what I'm showing here is substrate concentration on this axis, V naught concentration on this axis. Let's call this the normal non-inhibited state. If we add a drug that competes at the binding site, what that means is this curve will have a much flatter shape. I'm exaggerating that a little bit. A much flatter shape. But ultimately, it will reach the same Vmax. And that's because if I add enough of my drug, enough of the substrate, it will outcompete the inhibitor, it will displace the inhibitor, and it will get to full activity. But it's going to take more of my substrate to do that, right? To get to that concentration because the inhibitor is blocking the active site. And so the reason we say this leads to an increase in Km is if we go here and look at this, this is reflected in an increase in the Km, right? For our inhibitor-bound state, it's a much higher concentration of substrate required to get to half max activity. That means to an increase in Km. The other thing that's not always, but most often true is that if you're looking at a competitive inhibitor, it usually looks quite similar to the substrate. And it's basically because a competitive inhibitor has to bind at the same site, so it's going to look usually a lot like the substrate. Okay, that was a competitive inhibitor. What about non-competitive inhibitors? So here's an example of a non-competitive inhibitor taken from hepatitis C. So hepatitis C that has an RNA polymerase that binds to RNA in its active site. So it's basically when hepatitis C virus is trying to replicate, it needs to run this RNA polymerase, and it does so by binding RNA at that active site. But this is inhibited by this molecule over here, which binds away from the active site and inhibits activity. So we got one site that's distant from another site that's having an effect. This is an example of allostery. This drug is allosterically inhibiting the hepatitis C RNA polymerase. It's behaving allosterically. It's communication at a distance. And what this does is it actually has a different effect on the Michaelis-Menten curve. So this is S naught here. This is V naught here. Here's our normal curve. And what's happening here is what you're going to actually see is a curve that looks something like this. So a non-competitive inhibitor binds away from the active site. This leads to a drop in Vmax. And so the reason that you don't see a change in Km, you see a change in Vmax, is you're basically, there's a couple of ways to think about it. You're either taking the drug, go back to my picture of the enzyme. You're either taking the drug and you're putting it's putting the enzyme into an inactive form. So your E total goes down. The amount of enzyme around goes down. Or you're binding to your enzyme and you're just lowering its ability to do its activity. So your Kcat goes down. But your substrate can still bind fine. And so what this means is you end up lowering your Vmax, which remember is Kcat times E total. But your drug binds, or your substrate binds fine, so you don't see any change in your Km. Another rule of thumb about these is relative to competitive inhibitors is that a non-competitive inhibitor usually looks quite different from. And that's because they're binding at different sites, right? If you're going to go back 2 slides, this is binding very distant from that. And what this means is that a non-competitive inhibitor will usually look different from the substrate. Okay, one more inhibitor and then we'll summarize. The last inhibitor we're going to talk about is an irreversible inhibitor. A good example of this is saurin, which is a potent neurotoxin. And what saurin does is it covalently modifies the active site in acetylcholine esterase. So in neurotransmission, we have to dump out tons of acetylcholine. This basically ruins that biosynthetic pathway. And it does so because when the saurin goes into the active site, it starts doing a catalytic cycle. It actually undergoes, it does a nucleophilic attack, but then it never resolves. So if you think back to the serine protease, at one point there's the N-terminal peptide that was cut off, hanging off of the serine. Imagine if that never came off. If that never comes off, the enzyme never recycles back to its starting state, and you've destroyed the enzyme. And so an irreversible inhibitor covalently modifies the active site, destroying the enzyme. This leads to a drop in Vmax. And the way I would think about this is your total enzyme concentration is going down. So your active enzyme concentration, at least. Sure, you've got a bunch of enzyme proteins in solution, but most of them aren't working anymore, so your enzyme concentration goes down. So you see a lot drop in your Vmax. So what that would look like on this curve is the following. There's your normal. And there is your drugged. The inhibitor often looks quite similar to, not similar to the substrate, and that's because it's binding at the same site and destroying the active site. So what that lets us do is sort of construct a table for this. So a competitive inhibitor is going to lower the Km. It's doing so because it's competing at the substrate binding site. If you add enough substrate, you can outcompete it and you can put it into an active form. And so that effectively means that, the Km goes up. I said that backwards. The Km goes up. It's a higher Km. It takes more and substrate to put it into the, to outcompete the inhibitor. A non-competitive inhibitor is going to have the effect of lowering Vmax. You're either tipping the protein into a less active form, so Kcat's going down, or you're just putting a bunch of the enzyme into an inactive form, and so your enzyme concentration is going down. And then for an irreversible inhibitor, you see something very similar, that every time the enzyme binds, it destroys an active protein, so your total enzyme concentration is going down. There are some general rules. It's not quite these aren't fixed exactly, but general rules would be that competitive inhibitors are similar to the substrate because they bind at the same binding site. Non-competitive inhibitors are dissimilar because they bind away from the binding site. And the irreversible inhibitors are similar because, again, they bind at the same active site as the substrate. And so what this means is if you know some information, oh, look, the Vmax went down and it's dissimilar molecules, it's probably non-competitive. Whereas if it's Vmax goes down, it looks very similar to the normal protein, it's probably an irreversible inhibitor. Okay, so hopefully that gave you a flavor for how you can sort of query Michaelis-Menten curves with drugs to start learning about mechanisms of inhibition. It's a very commonly used thing inside of biochemical literature, a very common thing as you're trying to understand what's happening when you start manipulating metabolism or biochemical pathways with drugs. So hopefully that was useful, and I will talk to you later.